Hello. In this lecture, we'll continue with the notion of area of a region in a surface. And after that, we'll define gradient of a differentiable function on a surface. Let us begin. So first, let us try to find out a formula for area of surface of revolution. Okay, so let us take a real valued differentiable function. So let f, it is a real valued differentiable function okay, and also let us assume this f of x is positive for all x belong to AB. Okay, so let us take the surface obtained by revolving the graph of this f around x-axis. Let us take this to be my x-axis. So this is my y-axis and this is my z-axis. And suppose this is my graph of this fx, which is x comma fx, and the z coordinate here is 0. So this is my graph of fx. Now what I am doing, so I am rotating this curve around x-axis. So if you rotate, so then you'll get a surface of revolution. So we'll get this surface of revolution. Okay. And now let us take some closed interval. So let CD be a closed interval inside this open interval AB. Okay. So for this CD, this closed interval, I'll get a region inside this surface. Okay. So let S be the surface obtained by revolving the graph of f around x-axis, and let R be the region in S obtained by revolving the graph of f restricted to the closed interval CD around x-axis. Okay, so how to get the area of this region R? Okay, so now I can give a parameterization of this surface S. So let sigma x comma y. So this is equal to x fx cos of y fx sin of y. Yeah. So this x, it is varying in this open interval AB, and y, it belongs to 0 to 2 pi. Let us take it to be first closed interval. If I take this thing, so sigma of the set open interval AB cross closed interval 0 to 2 pi. So this will be equal to S. Okay. And sigma of this open set open interval AB cross open interval 0 to pi. So this will be an open subset of this S. Okay. All right. So now, so what is my formula for this area of this region? So area of this R, so this is this double integral over the region CD cross 0 to 2 pi norm of sigma x cross product with sigma y dx d1. Okay, so we need to compute this double integral. Yeah, so what we'll get if I compute this sigma x, so sigma x at the point xy, so this will be equal to, so sigma xy is equal to x fx cos y fx sin y. So from here, so what I'll get, sigma x xy, it is equal to 1 comma f prime x cos of y comma f prime x sin of y. So you'll get this thing. And sigma y xy, so this is equal to 0 minus fx sin y comma f of x cos y. All right. And this vector product sigma x with sigma y, so this will be equal to fx times f prime x. This is the first coordinate. The second coordinate is minus fx cos y, and the third coordinate is minus fx sin y. So you'll get this thing, and norm of this sigma x cross sigma y, so this will be equal to root over fx f prime x whole square plus fx square cos square y plus f square x sin square y. So you have this thing, and this is equal to fx multiplied by 1 plus f prime x whole square. Okay, so therefore, the area of this region R, so this is equal to this double integral. Okay, and in this case, so this double integral is equal to integration c to d fx root over 1 plus f prime x square dx integration 0 to 2 pi dy, and this is equal to 2 pi times integration c to d f prime 1 plus f prime x square dx. So we obtained a formula for this area of region of this type, which is obtained by taking a curve and revolving it around an axis. So now let us try to find a formula for a surface arising from a differentiable function from an open subset of R2 to R. Okay. So let f u to R be a differentiable function. So where this u, so this is an open set in R2. And also let us assume, so let us assume fxy is greater than equals to 0 for all xy belonging to u. Okay. And now if I take the graph of this function, so these are my coordinate axes. So this is x-axis, this is y-axis, and this is z-axis. And suppose this is my u. So graph of this f, it will be on this u. So it will be something like this. So this is graph of this f. So this is x, comma y, comma fxy, where this xy, it belongs to u. Okay. So let S equals to xy fxy, where this xy, it belongs to U. So then we know that, so this S, it is a regular surface in R3. And let us take sigma xy equal to xy comma fxy, where this xy, it belongs to U. So U comma sigma, it will be a regular surface patch. In fact, here sigma of U is equal to S. Okay. Now, how to get this area? I'll just write here S, or if you want to be more precise, you can take some closed region inside this S. So let me just write down area of S. So this is nothing but equal to integration, double integration on this set U, norm of the cross product sigma x with sigma y dx dy. And what is my sigma x? So sigma x is 1 comma 0 comma fx, the partial derivative of f with respect to x at the point xy. Sigma y is 0 comma 1 comma fy. And if I take this vector product, sigma x vector product sigma y, so this will be equal to minus fx comma minus fy comma 1, and norm of sigma x cross sigma y, so this will be equal to 1 plus fx square plus fy square. So therefore, we have a formula for this area of S. So this is equal to the double integral over U root over 1 plus fx square. So this partial derivative with respect to f is evaluated at xy plus f square y at the point f square y evaluated at the point xy dx dy. Okay. So therefore, we got this formulas. And now let me define what you mean by gradient of a surface. Okay. So let us start with a regular surface. So let S be a regular surface in R3, and if S to R be a differentiable function. The gradient of this map F is a differentiable map denoted by grad F. So this differentiable map, grad of F, it is a map from the surface S to R3. So what is the definition of this map? So this grad of F, which assigns to each point P belonging to S a vector grad of a P. So this belongs to the tangent space of S, which is again, it is a subspace of R3, such that the inner product of grad FP and an element W belonging to the tangent space is equal to the differential of F at the point P evaluated at the point W. Yeah, so this is my definition of this grad F. Okay, so grad of F, it is a map from this S to R3. And now if I take any point P belonging to S, so grad of FP, it belongs to the tangent space, and inner product of grad of FP with any vector W is equal to dFP evaluated at the point W. Okay. So this is the definition of this this grad of this this function. And let us see locally how does it look like. So suppose you are given a surface patch u comma sigma. So with respect to the this coordinate map sigma, how this grad of f it looks like. Okay, so let us take a surface patch such that sigma u is contained inside this S. And recall E du squared twice F du dv plus G dv square. So this is the first fundamental form of the surface. Okay, so where this E is equal to the inner product of sigma u with sigma u, F is the inner product of sigma u with sigma b, and G is the inner product of sigma b with sigma b. Okay, so we have this thing, and so also we know that so sigma u sigma b forms a basis of the tangent space. Okay, and grad of fp, it belongs to the tangent space. So this will be equal to linear combination of the sigma u and sigma b. So this will be equal to C1 sigma u plus C2 sigma b. Okay, so we'll find out this coefficients C1 and C2. So how to find this thing? So take the inner product of this grad fp with the coordinate vector sigma u. So what I will get? So we'll get C1 inner product with sigma u comma sigma u plus C2 inner product with sigma b with sigma u. So I'll get this thing. So which is nothing but equal to C1e plus C2F. Okay, so you'll get this thing. And similarly, grad FP, if we take the inner product with sigma B, so we'll get, so this will be equal to C1F plus C2G. So we'll get this thing. Okay. And now, so this inner product, grad FP with sigma U, by the definition of grad, so this is equal to differential of F at the point P of sigma U. Okay. And this is nothing but, so this by the definition of sigma U, so this is differential of F compose sigma evaluated at the sigma inverse P of del del U. So which is nothing but again equal to the partial derivative of F compose sigma with respect to U. So this evaluated at sigma inverse P. Okay. And let us call this to be equal to Fu. And similarly, what we'll get, the inner product of grad Fp with sigma B, it is equal to Fp. Okay. So therefore, so what we got two linear equations, C1E plus C2F is equal to Fu, and C1F plus C2G is equal to Fp. So we got these two linear equations, and from here we solve the C1 and C2. So what I'll get? So C1 is equal to G times Fu minus F times Fp divided by Eg minus F square. And C2 is equal to Fpe minus Fu F Eg minus F square. Okay, so thus this grad Fp, so this is equal to Gfu minus F Fp E divided by Eg minus F square sigma U plus Fb E minus Fu F divided by Eg minus F square sigma B. Okay, so yeah, so thus we got an expression of this grad of Fp with respect to the this local coordinate U comma sigma. Okay. So now observe this fact. So this, let us take, so let us take this set D to be equal to all those tangent vectors such that norm of B is equal to 1. Okay. So the observation is DFPB is maximum if and only if B is equal to grad FP divided by norm of grad of F at the point P. Okay, so how to show this thing? All right. So recall the definition of this grad. So DFP B is equal to the inner product of grad F at the point B at the point P with B. So we have this inner product. And now you take mod here. So this inner product, it is a real number. So you take mod here. And now you apply Cauchy-Schwarz inequality. So by Cauchy-Schwarz inequality, so what you will get? So this mod is less than equals to norm of grad of F at the point P times norm of this B. Okay. Now, B I have taken from the tangents from this D. So this will imply that norm of B is equal to 1. Okay. So therefore, on D, mod of DF at the point B is less than equals to the norm of the grad of F at the point P. So this is true for all P belonging to D. Okay. And now if I put B equal to, so let B equal to grad of this FP divided by norm of this grad FP. So what I'll get is the following. So DFP of this grad of FP divided by the norm. So this will be equal to the, by the definition of this grad of FP, this inner product, grad of FP with grad FP divided by norm of this grad of FP. So this will be equal to norm of grad of FP. Okay. So therefore, so what we have shown that, so DFP P is maximum if and only if P is equal to grad FP divided by norm of grad FP. Okay, so this is one fact, and let us prove another geometrical fact of this this grad of this F. So suppose this grad F is not equal to 0 for all points on the level curves C equal to Q belong to S such that f of Q is equal to constant. Okay. So suppose this is my surface S and I have a map f from S to R, and so I'm taking all those points Q belonging to S such that f of Q is some equal to some constant. Let us take it to be some C. So this is my this level curve, capital C. Okay. So the claim is the following. So grad of this FQ, where this Q, it belongs to C, is orthogonal to the tangent vector of the curve C at the point Q. Okay, so this we are going to show. Okay, so yeah, so let us take, so let alpha t equal to, so suppose if you have a curve C inside the surface S, and if I take any point here, so we can have some surface patch u comma sigma. So sigma u, it intersect the C. So let us take this alpha t to be equal to sigma ut comma vt belonging to C for all t belonging to this interval minus epsilon to epsilon. Okay. And now if I take this alpha prime t, so this is equal to sigma u du dt plus sigma v dv dt. So alpha prime is, it is a tangent vector. It will be of this form. And now we are given that f is constant on C. So f of alpha t is equal to constant. Okay, so this we are given. Okay, so this will imply that so this differential of this f at okay, so differential of f alpha t of this alpha prime t, so this will be equal to 0. All right, so this implies that, so in particular, differential of f at the point alpha 0 of alpha prime 0, so this is equal to 0. So this implies this grad of f at the point alpha 0. If I take this thing, take the inner product of this grad of f with alpha prime 0. So this is equal to 0. Okay. So this shows that grad of this f alpha 0 is orthogonal to alpha prime 0. Okay. So another observation I want to make here is the following. So this C is a regular curve. So C is a regular curve. Okay. So how do you show this thing? So let us take, so let sigma ub, it belongs to C. So what is my C? So it is all those q belonging to S such that f of q is equal to constant. Okay, so let us take sigma ub, it belongs to C. So this implies that f of sigma ub is equal to constant. Okay, and now let us take, so let f ub is equal to f of sigma ub, so which is equal to constant. So let us take this capital F to be this function. Now, so del f del u at the point sigma inverse or sigma inverse of sigma ub, so that will be ub. So this will be equal to df evaluated at the point sigma ub of sigma u. So this will be equal to grad of f at the point sigma ub, comma sigma u. So del f del v evaluated at the point ub, so this will be equal to grad of f of sigma ub, comma sigma b. Okay. So what we want to show that in order to prove that the C it is a regular curve, so this del f del u and del f del v, they are not both 0. Okay. So if one of them is not equal to 0, so by implicit function theorem, it tells that C it is a regular curve. So if del f del u at the point ub and del f del b at the point ub are both 0, then so this grad of f at the point sigma ub, so this will be equal to 0. Okay. So this is a contradiction. So as we have assumed, so as grad of f is not equal to 0. Okay. So this we have assumed. So therefore, so one of del f del u is not equal to 0. Okay. So by implicit function theorem, so it follows that C is a regular curve. Okay, so I'll stop here.